Okay, so this question is asking us to give the reducible representation for the motions of the following water molecule, H2O, and the problem went ahead and gave us the assigned Cartesian axes. So from that we can see that the z-axis is going directly through the oxygen molecule, and the x is going up, so x and z axes are in the plane of the paper with y coming out. So there are a couple things we need to do in order to find a reducible representation. The first being that we need to determine the degrees of freedom of the molecule. And this is done using the equation degrees of freedom equals 3n, with 3 being the axes for each atom and n being the number of atoms in the molecule. In this case, we have 3 atoms in the H2O molecule. So we have right here, 3n becomes 3 times 3, which means we have 9 degrees of freedom. The second thing we need to do is identify the molecule's point group, and this is based on symmetry elements. So we can go through and using the decision tree provided, or just looking at different things, we can see, is the molecule linear? Yes or no? It is not, in fact, linear. So then we can ask, is it cubic? No, it's not. Is it Cn to Cn? Yes, it is. It does have that rotation axis. So then we look at, is NC2 perpendicular to Cn? No, we don't have that. So then we have to ask ourselves if we have horizontal mirror planes, or sigma h. In this case we don't, but we do have vertical mirror planes. This tells us that our point group is C and V, and because we know that the C2 rotation axis will rotate 180 degrees each time to get back to the original positioning, we know that our point group is C2V. Okay, now what do we do with this? Well, we need to generate a reducible representation table. So what we see right here, ignoring these, we can see that for C2V, we have 4 symmetry operations. E, which is the identity, C2, which is a principal rotation axis, sigma V through the XZ planes, which is a mirror plane, and sigma prime V through YZ plane, which is another mirror plane. So these gamma values are the reducible representation values. So in order to find the values for each of these, we have to go through and do a couple things. First of all, we know that for E, it's an identity operation, which means there will be no change in the positioning of the molecule. This is important because we know that as we apply symmetry operations along the X, Y, and Z axes and assign characters, if the atoms have the same placement after the operation, or atoms are in the same place, then the contribution will be cosine theta, with theta being the degree of change within the axis or rotation. And then if there's a different placement after the operation, every vector on the atom will contribute 0. So because E doesn't have any changes, we know that its contribution is equal to the degrees of freedom, which in this case is 9. So we have a value of 9 for that reducible representation. C2, we can go ahead and we know that the H atoms, looking over here with this C2 rotation axis through the oxygen, we know that the H atoms will maintain their positions, contributing 0 for all values and vectors. However, knowing that this C2 rotation is going through the Z axis, as it is, we know that Z will not have a rotation, but we do have movement. So we are going to be contributing cosine of 0 degrees, which is equal to 1. The X and Y positions, X and Y, are, however, going to rotate by 180 degrees each, which will equal -1. So when we add all these values together, we get an overall value of -1. We can do the same things for our mirror planes. And looking here, we have the XZ mirror plane going through the middle of the molecule, like cutting through the hydrogens as well as the oxygen. And this means that as we rotate, all of the atoms will have the same position, where X and Z don't move, so contribute 0 degrees. And the y-axis is reflected, so there is a 180-degree change. And this is because we are keeping the x and z axes constant for this mirror plane, so we can go ahead and plug that in and get an overall value of 3. You can do the same thing for the YZ mirror plane and see that both H atoms will move to new positions with this reflection, and so they'll contribute, but they will contribute 0 because they're not rotating. And then the x-axis, however, does rotate, so it will contribute cosine of 180 and get an overall value of 1. And we can then go ahead and plug those in, and we get our overall reducible representation table.